Hello, welcome to Stats 479 Lecture 12. So we're in the middle of the third module of this course. There'll be four in total. So this third module is on regularization, and in particular, so far we've looked at sort of ridge regression, which was the regularization was the squared L2 penalty. So today, and probably for the next lecture, we're going to focus on another very popular form of regularization, which is L1 regularization. It's also colloquially referred to as the lasso. That sort of stems from a paper back in 1996, which I'll provide a reference to in today's lecture. And in particular today, we're going to focus on, well, first going to kind of introduce where this notion of like the purpose behind L1 regularization, and then we're going to kind of talk about this in the context of our framework, and in particular talk about algorithms, and if we get time, move into a little bit of analysis to talk about potentially what are the benefits of this L1 regularization type of approach. So just to remind everyone of our general regularization framework, so it sort of stems from, as I mentioned earlier, it stems from we're solving an optimization problem where you add a penalty or a regularization term. So in the first two modules, we typically only saw like a negative log likelihood or loss function or data fit term where we minimized that. And that was the estimator we used. And we found that it had a lot of nice, properties that were seemingly kind of nice, like it was unbiased most of the time. And, you could say a lot of kind of nice things about that. But as we saw in the previous lecture, and as we're going to learn throughout, there are often times where it's beneficial to add a regularization term. So here lambda is the regularization parameter. So I should mention here that lambda is bigger than 0. It's always or bigger than or equal to 0. It could be 0 in principle, which would just give you back the negative log likelihood. So let me just write that clearly. So lambda bigger than or equal to 0. And then R of B is the regularization function. So just to remind everyone kind of what the main couple of purposes of regularization are, there are many, but we're really going to kind of see two benefits in this course. The first one is that, and we saw this with the ridge regression or squared L2 penalty, is that it potentially improves stability or reducing variance of your estimator. So remember that, rather than inverting your standard, X transpose X matrix, we were adding a penalty, which meant you got something that was always invertible. And that also reduced the overall variance. So when we looked at it from a mean squared error point of view, we saw that, you increased bias because you added a regularization penalty. We'll see that pretty much all solutions to regularization problems basically introduce bias because the regularization function biases your B in a particular way. And so you can potentially say that's a bad thing because we're introducing bias. But if that bias is actually, a bias that, is a good thing, then you're potentially reducing variance a lot because you're in some sense limiting how, what kind of estimator you can have. And lambda, kind of trades off how much regularization and how much data fit you have. So the bigger lambda is, the more regularization you have. And we saw that with in the case of ridge, in the case of ridge regression or the squared L2 penalty. And the other key point, which is also very related, is that the regularization function essentially biases your parameter in a particular way. So it incorporates some form of prior knowledge. And so what we saw in the case for squared L2 is that if you know that your B is its L2 norm is not too big or it's close to 0, then this regularization was pretty good. And we saw that in the mean squared error bounds as well, where the bias kind of was related to the squared L2 norm. But then you could, and so you got a bigger bias as the squared L2 norm got bigger, but on the other hand your variance got smaller, and so you're incorporating this prior knowledge. And so we're going to see what that looks like for the case where instead of looking at the squared L2 penalty, we're going to look at the L1 penalty. So just to give a bit of so the purpose of the L1 penalty is a little bit different from the squared L2 penalty. We're going to kind of see, hopefully get an idea of, or a part of an idea of this today, and then also in lecture 13. The key idea is that so we want a bias B to be sparse, and so what that means is that so B has many zeros, and this is not approximate zeros. This is exact zeros, and so why would we want to do that? Imagine P. The number of features is large, but only S of them are relevant to the response. And this is the kind of thing that you actually see a lot in modern statistical applications. So for example, again, a very good example to think about is genetics data. So there, you might have the gene expression for like thousands or even hundreds of thousands of different genes. And then you're looking to see the impact on a particular maybe genetic disease. So maybe it's, some like cancer or some mental disorder that you might be interested in. But even though you have, thousands or hundreds of thousands of genes, you might expect that only a few of them, like maybe 5, 10, 100 of them, are actually contribute to the, in a significant way to that overall response. And so, you might expect that a lot of the to capture the fact that the effect of many of the coefficients are either zero or negligible, you want to set a lot of those parameters to zero. So there's there's lots and lots of other examples in imaging, neuroscience, and many others where you have lots and lots of features, but you only expect a small number of them to be relevant. So here I've let S be kind of the number of relevant features, I guess, to the response, and P is kind of the total number of features. And we're going to see later that using the L1 penalty kind of allows you to do that. It allows you to kind of shrink a lot of the coefficients to zero, and we're going to kind of see how that's going to work. Okay, so let's introduce the framework, and then kind of talk about like that, and that'll also give us a sense of the purpose. So what does this assumption mean? So mathematically, sparsity represented as they often use this notion of an L0 norm, even though this is not actually a norm because it's not a convex function. Like it doesn't have the properties of a norm, like the triangle inequality and various and like that if you multiply by a constant, that constant gets multiplied out. So this is not a norm, but they sometimes just refer to it colloquially as a norm. So what it's saying is the number of BJs that are not zero is less than X. So here all we're saying is that indicator BJ not equal to zero is just 1 if bj is not 0, and 0 otherwise. So if we sum up all the p coefficients, we're saying that only s of them are non, or at most s of them are non-zero. Okay, and so s is going to be significantly smaller than p. Otherwise, it's sort of not very useful. And so a couple of other reasons why this is a good thing to do. Another reason is so another reason is that, from a scientific point of view, one of the key questions we're always looking for is we're looking for models that are interpretable. So if we go back to that example that I described of, the gene expression for hundreds of thousands of genes, and then you're looking at the effect of those genes on a particular genetic disorder, if you got a model which just said that all of the hundreds of thousands of genes kind of have a little bit of influence, that isn't very interpretable to a practitioner. What they kind of would ideally like to say is, okay, we can isolate some number of genes that you not only expect this to be true in practice, but you can kind of isolate some key genes to say, okay, maybe if we perform some interventions on those small number of genes, we can do something. Whereas if you kind of just take a very big model where P is really large, you're not going to kind of get this interpretation. So that's another argument regarding why this L0 norm is widely used. The other thing I kind of wanted to mention, for those of you who've taken previous statistics courses, you may also be familiar with this notion of model selection. And the reason I bring it up is that these kinds of structural assumptions, B0 and B1, are very related to model selection. So another kind of interpretation of this is that so there are P features or covariates, only S relevant, and so another way to think about that is that you have hundreds of thousands of genes, and say you think only up to maybe 10 might be relevant, then the question is, how do you choose the S relevant features? Okay. And so this can be interpreted as model selection problem, because the model you're trying to select is the choose S features out of P. And so therefore, what we have is P choose S models to choose from. Okay. And so big, so you might just, and so there were, prior or classical work involved, like you may have heard of, or you could look up two different very classical and still very nice criterions, which are the AIC or BIC, which work reasonably well when P is small. So this is the Akaike information criterion and the Bayesian information criterion, and they work pretty well.